Okay, so we're going to get started now. So welcome to the second recitation. So today we will be talking about Bomb Lab, which is currently out. So we will be talking about assembly, machine code. We'll be talking about GDB, which will be very, very useful to you for Bomb Lab. Giving a demo of using GDB to play around with a bomb. So the first thing, so downloading your bomb. So it's quite similar to Data Lab. You go on AutoLab, you download the handout, you download a tar, which contains all of the important stuff in it. The bomb is unique to you. Everyone gets their own special bomb. Dr. Evil has created 1 billion bombs, and he can continue to make many, many new ones. There are 6 phases in this bomb. They get progressively more fun. And you can only run these on the Shark machines. Do not try running the bomb on a non-Shark machine. It will not work. It will blow up. You will lose points. Please read the write-up before you start. So here's the write-up. There's some important warnings in it. So one of these here, warning, do not use the debugger to jump directly to a particular point in the problem. It will cause it to blow up. Similarly, do not use it on anything other than a Shark machine, because that will cause it to blow up. What other warnings do we have? Oh, do not submit any strings that contain apostrophes in them. That breaks the autograder for some reason. None of the correct answers will need to have an apostrophe. So make sure you read through this whole handout. It has lots of important information, both in terms of things that you shouldn't do, unless you want to lose points, and things that will help you, these hints here. So make sure you read that. Okay, so exploding your bomb will notify AutoLab. You lose half a point every time the bomb explodes, up to 30 points. So you do not want to do that. When you input the right string, it moves you to the next phase. So what you'll have is, each phase is unlocked by a particular string, which you can type in either on standard in, just inside GDB, or you have a text file which contains the strings you've solved so far so that you don't have to keep typing them in. So you get the executable, you get a README, you get some of the source file, but not all of it. And you're going to have to be looking at the executable to figure out how to actually solve these puzzles. So a little bit of review of assembly. So hopefully you talked about this in class, right? Does some of this look familiar so far? Yes? You've seen registers before? So yeah, so x86-64 has 16 general purpose registers that you can read to and or read from and write to. These registers have special meaning in certain cases. So your first register there, RAX, is the register that the return value of a function is placed in before the function returns. So at the end of every function, it moves the return value into EAX if it's not there already, and then it does a return. Your arguments to a function, the first 6 are passed in these particular registers, RDI, RSI, RDX, RCX, R8, and R9. If your function has more than 6 arguments, the other arguments are going to be placed on the stack. Back when everything was 32-bit, everything was placed on the stack. But now that we have all these registers here, we have 16 instead of 8. We can put some of them in registers, and that's great. The RSP is your stack pointer. So your stack pointer is going to keep track of where the boundary of the stack is. The stack will contain extra function arguments beyond those 6 that you needed to pass into a function. It will contain local variables for a function will be stored on the stack. Information about how to get back to the previous stack frame is also stored on the stack. Let's see. So each of these registers, you can see they're sort of split in half. It like says RAX and EAX. So RAX is the full 64-bit width register. EAX is the lower 32 bits of it. So if you just wanted to access a 32-bit register, you can use these names to get the lower 32 bits, and then it's like you're doing something in x86, the 32-bit version. So those lower bits on the left-hand side are the 8 registers that the original x86 specification had. And then we've extended them to 64 bits and added 8 more, which is great. It makes things run faster to have these extra registers. Registers are fast. Getting things from like the stack of memory is quite a bit slower. So having more registers makes everything run faster. Okay, so some things about, actually, are there any questions about registers here and what they mean, what they're used for? Yeah.
Is there ever a case where you just want to use 32 bits instead of all 64?
So one case where you might just want to use all of the 32-bit stuff is if you're writing a program that's going to run on a 64-bit assembly but does like 32-bit math everywhere. So if you took 122, you know that C naught uses 122-bit math, or uses 32-bit math everywhere. C naught, the 122 language, uses 32-bit math everywhere. So if you use all of the 32-bit registers to do everything that does math, then you get 32-bit numbers with the appropriate overflow and underflow behavior for 32 bits rather than those extra bits that you're never going to use. So that's one case. Any other questions about registers? Okay. So some assembly operands that you have available to you. So in assembly, one of the things you have is constants. So constants will start with a $sign. And so there you have a constant in decimal, -42, and a constant in hex, 0x15213b. So the hex constants, of course, start with 0x, and the decimal ones don't. That's how you tell the difference between them. And these can be directly in your program to be used by an instruction as they are. You also have the registers. So the way you specify registers in the assembly is with a % sign in front of it and then the name. So %ESI gets you, the ESI register, which is the lower 32 bits of RSI, and then %RAX gets you, register RAX, which is the 64-bit width equivalent of EAX. Okay, so and then these registers, what do they store? They can store a value, or they can store an address, which is really just a value with a particular meaning. It's a value referencing a location in memory. Okay, so, and then the other thing we have is we can actually have memory locations. So we can have parentheses around a register, which means go get me the value in that register. We can have a constant in front of it, which means go get me the value at that register plus whatever that constant offset is. Or we can have even more complicated forms like this one, where we're doing math with multiple constants, multiple registers to figure out where in memory we should be looking up a value. And all of these things, especially the particular meaning of the memory location ones, are in your textbook. I believe it's chapter 3. So if you want to know what all of the different forms, because there's more than just those 3, are, you can look that up in your textbook, and it will tell you what the valid forms are and what they compute to. So any questions about these operands, constants, registers, memory locations? These are sort of the basic building blocks of executing a program. Okay, so then one of the other things we have is we have the arithmetic operations. So we've got things like moves in assembly. So did you all see move in lecture? Yeah, okay. So one of the interesting things, so we're using the, I believe it's the AT&T format for assembly everywhere. And one of the things about the AT&T format is that can be a bit confusing is all of the instructions are organized with instruction, source, destination. So when you say move RBX RDX, that means move RBX into, or move RBX into RDX. So the new value of RDX is equal to the old value of, current value of RBX. So I mean, it's not too bad for moves. You move from left to right. It gets a little bit more confusing for things like add, maybe. So right here we have add of parentheses around RDX and then R8. So R8 is our destination. RDX with parentheses around it, is dereferencing a memory location as our source. So when you have these arithmetic instructions which have just 2 values, what it does is it takes the destination and does the arithmetic operation to it using the source. So what you get is a destination plus the value of the source. So in this case, that's R8 gets added to it whatever value is at RDX. And then the same thing with this multiply. So R8 is going to be multiplied by 3. And then we're going to subtract 1 from R8. And then we also have this instruction, LEA, L-E-A. So have you seen that one in lecture? No? Okay. So this one is, it stands for load effective address. And it's sort of an instruction concerning memory, because it gets you just the address without dereferencing. But it's also used as a little shortcut for arithmetic a lot of times. Compilers will assemble particular arithmetic expressions to this because what it does is it combines multiplying and adding into one instruction. So you can get interesting stuff. So here what we do is we take RDX and we add to it twice the value of RBX. And since we're not dereferencing this, we're actually using the values stored in those registers, not going to that location. Okay, so do we sort of see how arithmetic works in assembly? So, we have a lot of, it's all of the instructions, basic things you would expect. You've got move, add, multiply, subtract, bit shifts left and right, arithmetic and logical. You've got, all of the bitwise operations. Divide and mod are a little bit funky. They have a different specification where they actually only take one operand, and it always divides by the values in EAX and EDX, and then spits out the quotient to EAX and the remainder to EDX. So if you see divide and mod happening, you should look up the details on those because they work slightly differently than these. Yeah? Right, yeah, so it's...
You're adding addresses.
So, yes, so you're sort of adding the values in those registers, which if you're using it as a memory location would be addresses. But you can also just stick, whatever value you want in there that isn't actually a valid address and use this instruction to add them together or multiply them. Because both addresses and just integer values are, they're the same. It's just a 64-bit number. And the assembly language doesn't have any notion of types where it will distinguish between the two. So I could just put, I could put 5 in RDX and 10 in RBX, and then I'll get 25 out in RDX. Even though those wouldn't be valid locations in memory, most likely, to actually use. Any other questions? Okay.
So even though it's not actually dereferencing it's still getting a value. It's the equivalent to like add when the dereferences for RDX. That's getting a value in RDX, and here it's also getting a value in RDX. It just doesn't have like...
Right, yeah. So it puts that value in RDX, but it doesn't treat it as a memory location that then gets dereferenced to find out what's at that memory location. So it just gets you the address from this computation. So back here when we had something like this, we'd be doing math with RCX and RDI and some constants, and then once we got an address from that, we'd actually go to that location, and that's the value of this this expression. In the case of just load effective address, all it does is get that address. It doesn't go and get the value at that address. Okay, any other questions? Okay, so one of the other things we might want to do in assembly is compare numbers. That would be great. There's a couple different ways to compare numbers. So we have CMP. CMP will compute the value of A minus B, where A is the second operand and B is the first. And test BA will compute the value of the bitwise AND of A and B. And what these do is they do that operation and then they set some flags. So in addition to these registers, these 16 registers that you've seen, there's also some condition flags. that are being kept around as state throughout the execution of your program. And these two instructions are ways to set them. And then the jump instructions will jump conditionally based on the current value of the flags. So the pattern you'll see all the time is you'll do some sort of comparison, and then right immediately after there's one of the conditional jump instructions. So the comparison sets the flags, and then if the flags are right for the jump condition to be true, it'll jump to that address. Otherwise, it will just continue on to the next instruction. So in this case, what we have a comparison of R9 and R10. So what does it do? It does R10 minus R9, which sets some flags. And those flags are going to be interpreted so that if the comparison was greater, so if R10 was greater than R9, because remember these are slightly backwards from the order that would be a little bit more intuitive, then we're going to jump to the address 8675309. And if it turns out that R10 is less than or equal to R9, we'll just continue on to whatever instruction is immediately after that jump. So does that make sense? Pay particular attention to the order here, because this can get really confusing because they are exactly backwards from how you would normally read it. So here's the different jump instructions that we have available to us. There's the unconditional jump, JMP, that just always jumps. It doesn't care what the flags are, it doesn't care what else is happening, it just jumps to whatever address you give to it. And then there's all of the conditional jump instructions. So there's one that will jump if the two numbers were equal, not equal, greater than or equal, less than or equal for the signed values, and then some unsigned ones, so above, below, and then some ones based on the signed bit. So depending on what sort of math you're doing, all of these different jumps are useful. There's also corresponding set instructions that if you wanted to get the values of those flags into a register, they sort of line up with these, and you can take the values of the flags and dump them into one of your registers and use them for whatever in your program. Okay. So here's some practice problems. Okay, so, actually, any questions about the jumps? Okay, we'll do some practice problems now. So we've got CMP of this hex value and R12. So what's the condition under which this will jump to that address dead beef? Fill in the blank for the first one. So here's our little cheat sheet again. So JGE is jump if greater than or equal to. So what's the comparison happening?
R12 greater than or equal to 0x15213, jump to dead beef.
Right. Okay. So if R12 is greater than or equal to 15213, because the order is swapped from what we might expect, then we will jump to dead beef. Otherwise, we will continue to the next instruction. Okay. Yeah.
15 is what you know, address in memory.
So we've got a dollar sign there. So 15213 is a constant. So we are comparing whatever value is stored in the register R12 to the constant, the hex constant 15213, which I don't know what that is in decimal. It's some number bigger than 15213. And then dead beef is the address of the next instruction that it will jump to. Okay. So then the next one. Okay. So we've got JAE now. So what was JAE? So JAE is the unsigned equivalent of greater than or equal to, which we call above or equal to. Okay. So then what's happening in the second one? What comparison are we doing that will make this jump true if the comparison holds? Any guesses? Yeah. So we do the uncompared, the unsigned RDI minus RAX, and so then if the unsigned value of RDI is greater than or equal to the unsigned value of RAX, we'll jump to this 15213B. Otherwise, we'll continue on to whatever instruction is after that jump. And now we have this last one, so test. So we had the compares, and then we had test. Test was the one that just did a bitwise and. And then this jump condition is not 0. J and Z. Jump not 0. So, okay, so we're testing if R8 bitwise and R8 is not 0. When is that going to happen? Whenever R8 is not 0. So what this comparison is actually doing is it's just checking R8 not equal to 0. And if R8 is not equal to 0, then it's going to jump to the address stored in RSI. We have parentheses around it, which means dereference. So we go to RSI and we look at whatever address is stored in it, and we jump to that location. Otherwise, we just continue on to the next instruction. So does that make sense to everyone, why these 3 things are the 3 that they are? Okay. Good. So let's talk about Bomb Lab some now. So there's a couple different utilities that will be very useful to you as you go through your Bomb Lab. So what I have here, I've downloaded a bomb. You're going to get some bomb, and it's going to have a number. Can you see that at all? I think these... Can we turn off that light? There we go. Okay. I will. How is that in terms of size for everyone? Good? Okay. So we've got a couple different programs that will be useful to us as we are playing with our bomb. So the first one here is objdump, or obj dump, or however you're supposed to pronounce it. So this has a couple different flags that will change what it does. So the first one is the -t flag, and that will give you the symbol table for an executable. Okay, so what, let me remove that because that won't come with yours. So what you get when you unzip or untar your tar is you get a bomb executable, source file, and a README. So if we look at the source file, just real quick, what we see is that it's got a little bit of sort of the skeleton of the program. You can see that we've got initialized bomb, and then we run phase 1, 2, 3, 4, 5, 6, and Dr. Evil prints out some taunting strings at you as you go, and hopes that he's able to stop you with one of these. This is all the source code you get, though. There's obviously a lot more going on than this because you don't get the actual source code for what phase 5 is or what phase 1 is, just the fact that it's being called. So this is useful to read, just so that you sort of know the high-level control flow that your bomb is going to be going through. But you'll need a little bit more than this to understand what's going on. So we have the bomb executable, and that actually is the code that's going to be running. So in there is all of the information you need to know what's actually happening. So one of these programs that will be helpful to you is this objdump program. So -t will give you the symbol table, and you give it the executable. And I'm going to pipe it to less just because there's a lot of output. You could also just have it dump it all into your terminal or pipe it to a file if you wanted. Okay, so what do we get? So we know that we have a bomb, and it's going to give us a bunch of information about all of the symbols in this file. And maybe I'm a little bit, yeah, that's better. Can you still read it? Just so the lines don't wrap as much. So we've got interesting things in here. We see there's like a .text and a .data and a .bss, and those are things that are actually in all of your executables that you'll learn about in this course. So far, none of this is particularly interesting. Oh, look, it calls malloc sum. We can see that. What else does it do? It's got some locking and unlocking. What else does it do? Check free. A lot of this seems like it might just be system calls. But in here are all of the function names and interesting things that will be in our bomb. So maybe we should just search for the string bomb because Dr. Evil seems to like naming things like that. So let's see. So we found that there is actually a function called initialize bomb. That's useful to know. What else is there? Initialize bomb solve. Explode bomb. That one's very interesting. So there's a function called explode bomb. And I'll give you a hint. That's the function that explodes the bomb. It's not a trick. That actually is what it does. And in fact, that is actually the only way the bomb will explode unless you disobey our instructions and try to jump directly to something or set values in some funky way that gets around actually solving the puzzles. If you solve them correctly, the only way the bomb will explode is if you go through explode bomb and it executes. So that's something very interesting. So let's exit out of that. You can take some time to look through yours a little bit more closely and see what else is in there. There is plenty of interesting stuff in there. Okay, what else do we have? We have the -d flag for the same program. So the -d flag will disassemble a program. And I'm going to pipe this to a file and open that up. So, okay, so what do we have? So we've just disassembled our bomb. And now we get to look at all of this beautiful assembly code. And in this file is all of the information on what the bomb does. So, you could just like read through this file, and if you understand it, then you'll know exactly what to type in, right? Except that's kind of hard. So we're going to want to be using GDB2, and I'll show you that shortly. And that will actually let you play with stuff interactively, which is a lot easier than just reading assembly. But this is useful. So we see up here we've got what looks like a bunch of system calls of some sort of boilerplate that's not actually specific to the bomb. We've got something with malloc. But we know that we had this function called explode bomb. So we can sort of look for that. Here's a place where it's called. It's called from phase 1. So here we found the assembly for the function phase 1. And we can see, it starts by changing the stack pointer, and then it does some moving, and then it calls some function called strings not equal, which is interesting. And then it looks like if you do the wrong thing, it'll call explode bomb. Otherwise, it will jump over that. See if this comparison succeeds, then it jumps to 401397. Oh, and look, 401397 is this line here, which is after the call to explode bomb. So if you got that comparison right, you won't explode the bomb on this phase. We can keep going. So all of the phases seem to be calling explode bomb. That's not surprising. Here it is. OK, explode bomb. So this is actually the assembly for explode bomb. So we could see what explode bomb does. My hint is that you should probably just keep your code from ever going into this function at all. There's really nothing useful you can do by going partway through explode bomb and then trying to get out later. OK, so that's explode bomb. We had phase 1 up there, which was interesting. And here's phase 1. So this is sort of what you want to look at to figure out how to get through phase 1. And so, we can look through all of this assembly as much as we want. There's lots of great things in here. There's also the function called strings. So strings will give you all of the printable strings in an executable. I'll pipe it to less again since there's a lot of them. And some of these are like complete gibberish. Like, what do all of these mean? Who knows? But if we look through this, it looks like we found some of the error messages that are in the program. That's interesting. So we can sort of just look through it and see if there's anything meaningful in our bomb that might help us out. And we keep going. Eventually, here's some more interesting stuff. So let's see. So okay, these. It looks like we've got some code of some sort here. Maybe that would be useful. Maybe not. Just a bunch of different messages. So, and there's my Andrew ID down at the bottom. Apparently he's in the bomb. So now you can sort of look through this to see all of the printable strings. And maybe some of them will be useful to you. This is an easy way to get at all of them. And then, of course, there's the tool that you'll be using the most for this lab, and that's GDB. So, okay, yeah, so that's those three. Now we've got GDB. So the way you open GDB is GDB. This stands for GNU debugger, by the way. So GNU being the same GNU from the GNU compiler collection, GCC, or GNU Emacs, or also the same GNU that's responsible for LS and cd and pwd and pretty much every function you use on Unix, except for the kernel itself. Okay, so GDB, and then you give it the name of the executable. If you don't give it the name of the executable and then you go into it and hit run, it'll just complain at you that it doesn't know what to run. So this opens up GDB for the bomb. And so there's a couple different useful commands that you can use in GDB. One of the ways to learn what all of the commands are is to just type help. This will be very useful to you to learn what different things you can run. So right now it's going to tell me that there's a bunch of different classes of commands. There's so many of them, it wants me to tell what sort of thing I want help with. So how about I want help with breakpoints? So I can put help breakpoints, and that will tell me the different commands relating to breakpoints. And there's many of them. So it tells me that one of the commands about breakpoints is called break, which sounds really useful. I'd like to be able to set a breakpoint. So if I type help break, I can actually then even get more information, more information on the specific function called break. So it tells me that the correct syntax is break and then a location, and then optionally I can add some more, an if condition or a thread number to that. Okay, so what do I want to do? So here's another hint: is tab complete works in GDB. So if I type br and then hit tab, it'll fill it out to break, because that's the only other thing it can fill out to at that point. So what's the first thing I want to do? I don't want to explode the bomb. So I'd like for my program to stop before it explodes the bomb. And so the way we're going to do that is we're going to set a breakpoint at explode bomb. So the function explode bomb, and once again, we've got tab complete, so I can just start typing, and then once there's no other function with that name, I can hit tab and it'll fill it out. And I hit enter, and it tells me there's a breakpoint at 0x401A14, which happens to be the location of the bomb, the explode bomb function. So now, anytime I'm running GDB, if it gets to this function, it will stop. And it will wait for me to tell it what to do next before continuing on and exploding the bomb. That's a great thing to have. So let's say I just go ahead and start running into that point. So the way to start it running is just run. Okay, and it's giving me a message from Dr. Evil. So it's right now waiting for a string. And that's going to be the solution to phase 1 that I'm trying to put in. And so I think maybe it's just like bomb. Who knows? Maybe he'd set it to that. So I hit enter. And oh, look, what happened. It continued to run after I put in that input. And it stopped on my breakpoint. So that means if I continue on from this point, it's going to go into the explode bomb function and explode my bomb. And that's bad. I don't want to do that, because then I lose half a point. And I don't want to lose half a point, because why would I want to lose half a point? So what do we do? So we can actually just start running it again from the beginning. And run will let us start running it again from the beginning. So now we're back to this point. But this is kind of useless right now. I would just I could keep guessing passwords, but I'm not going to guess it by random chance. It would take forever. So you can use Control-C if you want to get out of GDB entirely, or is it Control-D? Okay, you can use one of the two. And then I can go back in. And my breakpoint is gone now, because I exited GDB and came back. So I want to set it again, because I don't want to explode the bomb. This is really the first thing you should do every time you open up GDB for this lab, is type break, explode bomb, enter. And if you do that, and then don't continue on past that breakpoint, it's possible to complete this lab without it ever exploding. Even if you don't know the answer to the puzzle on your first try, it'll stop at explode bomb. You can start over, keep working on it, and not explode the bomb. But what I really wanted was, I wanted to get into phase 1 and figure out what was going on there, right? Because it just, went straight to explode bomb and didn't stop, at phase 1, so I could figure out what was going on inside. So what I can now do is set a breakpoint at phase 1, because I saw in the, assembly file when I opened it up that there was a function called phase 1 in there. So now I've set a breakpoint there too, and when I run it again, it'll come and it'll ask me for some input. And now what it does is it stops in phase 1. So there's a couple other functions with GDB that would be useful for me to use here. So one of these functions is disassemble, or just DISAS is the shorter form of it. So when I run that, what happens is it gives me the disassembly for the function that I'm in right now. So this is the assembly code corresponding to phase 1. And we saw this over in that other file. This is actually, it's really the same thing. But now we can see it right here in GDB as we're looking at everything else. And this is, these things are in the PDF, by the way. So we can see the disassembly here. That's cool. Yeah?
I don't get why don't you choose disassembly phase 1? Is it because you put a break in phase 1?
It's because that's the function I'm in. If we did help on the function, then we can, let's see. So the default is function surrounding the program counter of the selected frame. So that means that whatever function I'm in, beginning, end, middle, it'll just show the function for show the assembly for that function. Let's see. So we can give it an address and get the function surrounding that address. We can get a whole range if we want. We can also use the /m to get the source, it says, maybe. You probably don't have the source for this function. It doesn't have any source for this function. But you can, whatever range you wanted, you would figure out what addresses they're at, and you can give it that range according to the help file, and it will disassemble all of that for you all at once. Any other questions about this so far? Okay. So this is okay, but so far we haven't done too much more than what we were able to do with just the obj dump, because we were able to see this. What's really useful is that we can actually see the values at different memory locations and the value in different registers as we're executing our program. So we can sort of take it one step at a time, or however many steps at a time we want, and then pause it and just take a look at what everything is, figure out what's going on, and keep going from there. So you've got info registers. And what that will do is that'll print out the values in all of your registers at the moment, and also some of the flags. So what we can see here is all 16 of those registers. They've got these values in them. We've got the instruction pointer is at that particular instruction. RIP is the instruction pointer. And then we've got some flags set to some particular values. Maybe we don't want to see all of the registers at the same time. Maybe we only want to see some of them. We can do that by printing out a particular register. And it is $ in GDB to prefix the register, which is kind of strange considering that in the assembly $ was for constants and % was for registers. But with the print function, it's $ register name, and that's the way it works. And of course, you can always use help to figure out exactly what a function wants if you're not sure. So this is printed out for me, the value in RSP. And there's another function. We've got step I, which will just step an instruction. So I can do that. Okay, so I've stepped one instruction. We look up here, we can see that we're now at this instruction. It gave us our new program counter. So we've executed this. Subtract 8 from RSP and store that in RSP. And so if we do another print of RSP, we see that indeed the value of RSP has been decreased by 8. So we can sort of use these printing functions and info and such to figure out what the different values are in our program as we go along executing it. And we can stop it at any point and look up what everything is that we want to know. So that was the step I instruction. Step I just in steps, a single instruction. We can run that multiple times. You can also just use SI, does the same thing. Okay, so what else do we have? So info registers, we've shown that. We've shown printing. Then there's X. So X is the examine command. So what's the format for X? So we can give it an address or a register. So if we want to examine what's at RSP, now we can actually see, we can see this way what's the value at RSP. So it tells us where RSP is and that its value is this constant here, 004031A0. And maybe we want to see like multiple things. So there's these different formatting options. So we can see like 4 words in decimal at this value. So then, we get those. And so now you can sort of like print out ranges of memory and see what values are in them, using a register or an absolute location, as where you're going to start from. You can see, all of the values of the registers. You can see the assembly, what the assembly is, where you are. And so doing this, you can sort of step through the program, setting breakpoints, stepping one at a time, whatever you need to do, and sort of start to reconstruct what's going on with this bomb. Because all of the information is here, of course. The computer has to know what to do. And all of that information of what the computer has to do is stored in the assembly. So as you step through it, the information for what you need to do to make it not go into the bomb function is there somewhere. You just have to sort of reconstruct it from this low-level representation, since you don't have the source code available to you. So any questions about GDB so far? The functions you've seen, how to use it, how to figure out how to use it when you don't know how to use it. There's also, there's plenty of tutorials for GDB online, but one of the most useful things will just be this help command. And if anytime you want to see a list of things available to you or how to use them, this will tell you exactly how to do that. No questions so far? Okay, so we can play around in our in our bomb a little bit more. So let's see. So where were we? Oh, so we've somehow made it into the function strings not equal. Apparently, I stepped enough times that I ended up in that. So now we get to see the assembly for strings not equal. And so this is obviously this is something important for the first phase of the bomb. And once it's checking if 2 strings are not equal. It's going to be up to you to figure out exactly what string is checking for this inequality, so that you can put in the correct string that it will not explode. But we can see here that we could step through this function and sort of look at the different calls that it's making and the different comparisons that it's making. We talked about what these different comparisons mean, JNE. There's another JNE. And then, of course, call Q is the assembly instruction for calling a particular function. And here it's calling string length or strings not equal again. Or no, those are jumps. It's calling string length is the only thing it calls. So, we can sort of figure out what's going on. We see here that at the end it moves the value of EDX into EAX. As we said, EAX has to contain the return value. So that's what that instruction is doing, is it's making sure that EAX has your final return value, which if you get down to here is going to be 1, it turns out. If the compiler was a little bit smarter, it probably would have moved 1 straight into EAX because, why did we put in EDX at all? But sometimes compilers do weird things like that. And, and then we pop some stuff off the stack. You should read up in the book about, stack discipline if you want to know what's going on there. That's all in the book of how the stack is managed. And then we return to the calling function. So we could step 1 instruction at a time through this. And now, now we've entered the call into string length. There's also a function called next. Next should jump over the function calls when those are reached in a single step. Or we could just, keep going until we hit the next breakpoint. Or until we exit the function, actually, is what that one does. So, now we're back. We're back in our calling function. So do you sort of see how you're going to step through this and everything? Yeah? So yeah, so, we can keep running this. So one thing that you don't want to do is once you get to this explode bomb, is just keep going, because then the bomb blows up. So here's, just in case you're curious, this is what it looks like when the bomb blows up, because you probably don't want to do this yourself, just for the sake of, figuring out what it looks like. I'll save you the trouble. It will print out a message saying, boom, the bomb has blown up, your instructor has been notified, and this automatically posts to AutoLab with a half-point deduction. So right now I'm losing half a point on AutoLab. If you happen to only blow it up exactly once, you won't lose any points, because we'll be generous and truncate that value for you. But there's the notification. If you try doing one of the things, such as jumping directly to an instruction or running it somewhere off of the Shark machines, you might not get this notification. You might just lose the point. And that would be unfortunate because you might not know what's happened until you go back and check AutoLab. So read the handout carefully. Read the handout carefully and don't do any of those things that we told you not to do. And otherwise, put a breakpoint at the explode bomb function and don't continue running the program once you hit that. Start again from the beginning or exit GDB entirely and set the breakpoint again the next time you come in. Okay, so that's Bomb Lab. That's GDB. GDB, the thing about GDB is it mostly just takes some practice to get used to reading the assembly and running through GDB. It's not a particularly complicated program, though. This sort of core set of instructions here that we've listed on the slides are the ones that will be really useful to you. And of course, there's other ones too. I could actually show you. You can get like the call stack, the backtrace of a call stack. So if we looked at help, this would be under help stack. Maybe that'll be useful to you just if you want to know how you got to the point you got. All sorts of stuff like that. But these are the core ones that will be useful to you. The bomb uses scanf for reading strings as scanf. So you might want to look up how scanf works. And you can do that with man. So man will tell you all about scanf and sort of how the arguments to it are formatted. That'll be useful to you. If you get stuck, please read the write-up, read Chapter 3 of your textbook, view the lecture notes, view the course FAQ on the website. We have office hours. The exact times are posted on the website, but they include every Sunday through Thursday, 6 through 9, plus extras. Use man to figure things out. Yeah. Okay, any other questions before we end? Yes?
AutoLab is showing something really weird, where it's like phases diffused, and then everyone has one explosion, like 1.0 explosions. I'm assuming that's just an issue.
Everyone has 1.0 explosions. That's probably not true.
It adds your explosion score to your actual score for your overall phase diffuse score, and everybody has a 1 for explosion.
That's weird. I don't know why that is. Yeah, I'm not sure why that is. We'll see if we can figure out what's going on. Any other questions? Okay, good luck with your bombs.